I want you to just close your eyes for a second. Imagine you were sitting in a small, cramped office in Boston.
Right.
It is September 2nd, 1859. The room smells like stale tobacco, maybe some dust, and ozone. You are surrounded by brass machinery, coils of copper wire, and that rhythmic clicking of the telegraph.
Which is really the Victorian internet.
Exactly. It is the absolute cutting edge of human technology at the time. You are a telegraph operator. You are the master of the digital world of the 19th century.
And up until about an hour ago, everything was working perfectly. You tap a key, a circuit closes, and a message travels instantly down the line. It is just simple, reliable physics.
Right. But today, the physics has changed. You are sitting there, maybe sipping some lukewarm coffee, and suddenly your equipment starts acting up.
Just completely on its own.
Yeah, the sounder, the part that actually clicks to make the message, it starts chattering. You haven't touched the key. The receiving operator in Portland hasn't touched their key either. But the machine is just going haywire.
And it is not just noise. It is actual violence. The machine is behaving as if it is being driven by a ghost.
It is so crazy. So being a diligent operator, you reach out to adjust the tension spring on the relay key, just to stop the noise. Your finger brushes the brass and crack. You get thrown back in your chair.
A severe electric shock jolts right through your arm.
You look at the equipment, and there are sparks literally jumping between the contacts. The paper tape that records the dots and dashes, it starts smoking and actually catches fire.
Which is just, that is the moment the world changed, even if the people in that room did not quite realize the scale of it yet.
And it gets even stranger, because going through the historical archives from the Science History Institute, there is a verified record of a conversation from that morning between an operator in Boston and one in Portland, Maine.
Right, the one where they realize their batteries are surging.
Yeah, the equipment is becoming dangerous. So the Boston operator taps out a message saying something like, "Let us cut the power, disconnect the batteries entirely."
Which, in 1859, should have been the absolute end of the line. No battery, no current, no message. That is just how electricity works.
But it did not stop. They disconnected the power sources, physically removing the batteries from the circuit, and for the next 2 hours, they held a conversation.
It is wild.
They were tapping out messages using nothing but the currents in the air. They actually noted that the signals were stronger and clearer without the batteries than with them.
That is such a haunting image to me. The Victorian internet, powered not by chemical batteries, but by the sky itself.
At the time, they said it felt like the machines were possessed by demons. They were utterly terrified.
But it was not demons, it was the sun. They were experiencing the direct, raw impact of the Carrington Event.
Welcome to the deep dive. Today, we are unpacking that event, which is the most powerful solar storm in recorded history.
And we are not just doing a history lesson here today.
No, definitely not. We have a massive stack of research we are pulling from. We have got papers from Aalto University on geomagnetically induced currents. We have got the historical archives we just mentioned. And we are going to look at mission documents for the European Space Agency's Vigil spacecraft.
And the reason we are looking at this specific stack of sources is because those demons from 1859, they have not gone away.
Not at all.
If anything, we have just built them a much bigger, much more expensive playground to destroy.
That is the mission for this deep dive. We need to understand exactly what happened in 1859, why a similar event today would not just burn a few fingers, but could cost trillions of dollars and basically collapse modern civilization.
And we also need to cover the truly terrifying discovery of something called Miyake Events.
Yes, which suggests Carrington was not even the worst-case scenario.
And, crucially, we are going to look at the solution. Because for the first time in history, we actually have a plan to stare down the barrel of the gun, the Vigil mission.
So let us go back to the scene of the crime, September 1st, 1859, the day before the Telegraphs went possessed. Who is the man this whole event is named after? Who was Richard Carrington?
Richard Carrington is a fascinating character because he really bridges the gap between the amateur and the professional. He was not some dusty academic locked away in a university tower.
Right. He was the son of a wealthy brewer.
Essentially, yeah, he had that kind of independent wealth. He had the resources to pursue his passion, which was astronomy, without having to answer to anyone or apply for grants.
He built his own private observatory.
He did, at Red Hill, near London. And while everyone else was looking at stars or planets or comets, Carrington was just obsessed with the sun, specifically sunspots.
Those are the dark patches on the surface, right?
Correct. And at the time, the leading theory was actually quite wrong. People thought they were holes in the sun's luminous atmosphere, revealing a dark, cool surface underneath.
Wow.
Yet we know now they are intense magnetic knots. But Carrington just wanted to map them. He wanted to understand their movement. So every sunny day, he is out there.
And he is not looking directly through the telescope. Right?
Oh, no, never. He projects the image of the sun onto a white screen, because you never look through the telescope directly unless you want to go blind. And he traces the spots.
It sounds almost meditative, just drawing the sun every single day, waiting for it to change.
It was, until 11:18 a.m. on September 1st. He is sketching a massive complex of sunspots. And suddenly, two beads of intensely white light appear right inside the dark spot.
White light, like brighter than the rest of the sun.
Much brighter, brighter than the photosphere itself. He was so confused that he actually thought a ray of sunlight had leaked into the room through a crack in the roof.
So he is checking his setup.
He checked his equipment, no leak. He looked back at the screen, and the lights were growing. There were these kidney-shaped, brilliant white patches. They were actually moving.
He was watching an explosion.
He was the very first human being to witness a white light solar flare. This was an explosion, releasing the energy of millions of nuclear bombs all at once.
And he ran out to get someone, right?
Yeah, she ran out of the room to find a witness, someone to confirm he was not crazy. But by the time he got back a minute later, it was already fading.
Okay, so he sees the flash, but the flash is not what burned the telegraphs, right? Because light travels fast.
No. And this is a really important distinction we need to make early on, because it is critical for understanding how we warn people today. The flash is just light. It is radiation, X-rays, and UV.
And that travels at the speed of light.
Exactly. So it hits Earth in about 8 minutes.
Okay. So by the time he saw it on his screen, the X-rays were already hitting our atmosphere.
Yes. That initial flash causes radio blackouts on the daylit side of Earth. Maybe messes with the ionosphere a bit. But the real danger, the bullet, that comes later.
The coronal mass ejection.
The CME. When that flare went off, it did not just flash. It vomited billions of tons of solar plasma and magnetic field out into space. It is like a shotgun blast of magnetized matter.
And it was aimed right at us.
Dead center. Now, usually, a CME takes 2 to 4 days to cross the 93 million miles to Earth. It is fast, but it is a long trip through the vacuum.
But the Carrington CME was different.
Very different. It got here in 17 hours and 40 minutes.
17 hours? That is incredibly fast.
It was moving at over 4 million miles per hour. And the reason it cleared the distance so fast is because a previous smaller storm had actually occurred just days before and cleared the path.
Like a snowplow.
Exactly like a snowplow. It created a highway through the vacuum of space, a rarefied channel where the drag was just much lower.
So Carrington sees the flash at noon. He goes to bed, probably wondering what he just saw. And then the bullet hits.
And the sky catches fire. We have accounts from all over the world. Usually, you see the aurora borealis, the northern lights in high latitudes, Norway, Alaska, Canada.
Well, it is a polar phenomenon.
But on the night of September 1st and 2nd, the auroras were seen in Cuba.
Cuba?
They were seen in the Bahamas, Jamaica, El Salvador, and even Hawaii.
Auroras in the tropics. That does not even compute. That is like seeing a blizzard in the Sahara.
The sky was described as a blood-red crimson. Out of the Rocky Mountains, the light was so intense that miners actually woke up at 1 a.m. They got dressed, started the coffee, and began cooking breakfast.
Because they thought it was dawn.
They completely thought the sun had risen. Birds started chirping.
Imagine the confusion. No internet, no news, no way to check NASA on your phone, just the sky turning red in the middle of the night.
There's a report from a newspaper in New York where people were standing on the rooftops, reading the fine print of the street ads by the light of the aurora alone. It was beautiful, but it was also a sign of extreme violence.
Violence in what sense?
Magnetic violence. See, the Earth has a magnetic shield, the magnetosphere. It protects us from the regular solar wind. But when the Carrington storm hit, it did not just tap on the door. It crushed the shield.
It compressed it.
It compressed the magnetic field lines until they snapped and reconnected.
And that is what caused the telegraphs to go possessed.
Exactly. This is where we get into the physics of the why. The Aalto University papers outline this perfectly. It is Faraday's law of induction.
High school physics callback time. Refresh my memory because I'm pretty sure I failed that test.
It is pretty simple in principle. If you take a magnet and move it quickly over a conductive wire, you create an electric current in the wire. You do not need a battery. The movement of the magnetic field pushes the electrons.
Okay. So a moving magnet equals electricity.
Well, a solar storm is a massive moving magnetic field. And the Earth, the crust, the oceans, they conduct electricity.
Right.
So when a storm slammed into us, it induced massive electrical currents. We call them GICs, or geomagnetically induced currents. and they went directly into the surface of the planet.
The ground itself became electrified.
Yes. And electricity always seeks the path of least resistance. In 1859, the ground was rocky and resistive in a lot of places.
Yeah.
But humans had just laid these beautiful, long copper telegraph lines stretching for hundreds of miles.
They were basically giant antennas.
Exactly. The current that was supposed to be struggling through the ground said, hey, look at that copper. That is way easier. And it jumped into the wires. It rushed up the line into the telegraph stations and zap.
Okay, so in 1859, this is mostly a curiosity. It is a, wow, nature is powerful kind of moment. We lost some messages. Maybe a few operators needed some burn ointment. It was a bad day for Western Union, but life went on.
Because we were a civilization of muscle, wood, and scheme. The telegraph was a luxury. If the telegraphs went down, the train still ran, the food still grew, the water still flowed, and people still heated their homes with coal or wood.
But we do not live in 1859 anymore.
No, we do not. We live in a civilization of electricity. We have built a machine that covers the entire continent, the power grid. And if a Carrington event happened today, we would not just be seeing cool lights and getting some static on the radio.
You would be facing the collapse of modern infrastructure.
Absolutely.
Let us drill into that, because collapse is a word that gets thrown around a lot in disaster movies. What actually happens? We have these GICs, these ground currents. How do they break the grid? Do the lines themselves just melt?
The lines themselves are usually fine. They're designed to carry high voltage. The vulnerability is in the backbone of the grid, the extra high voltage transformers, the EHV transformers.
The really big gray boxes you see in the substations.
The ones the size of a house.
Mm-hmm.
These things are the beating heart of the grid. They step up voltage to push power across the country, and then they step it down so you can actually use it in your home.
Right.
Now, these transformers are designed specifically for AC electricity, alternating current. The electrons wiggle back and forth 60 times a second.
Like a pendulum. Tick-tock, tick-tock.
Right. But GICs, the currents coming from the solar storm, they are effectively DC, direct current. They do not wiggle. They just push, like a fire hose.
So you are shoving a fire hose of DC current into a delicate machine designed for an AC wiggle.
And that leads to a phenomenon called half-cycle saturation.
Mm.
It is a bit technical, but think of it this way. The transformer has a massive magnetic core inside it. It flips its magnetic field back and forth with the AC current.
Okay.
But the DC current from the storm pins that magnetic field in one direction. It essentially locks it up.
It jams the pendulum so it can only swing one way.
Exactly. It jams it. And when the core saturates like that, the energy has nowhere to go. It spills out as heat. Massive, massive amounts of heat.
So it starts cooking.
It cooks. And the transformer also starts to vibrate physically. Operators who've been near them during smaller storms say they emit this terrifying groaning hum.
Like it's screaming.
Yeah, and then it cooks. The copper windings inside, which are as thick as your arm, they can literally melt. The oil used for insulation boils. We're not talking about a fuse blowing that you can just flip back on. We're talking about the physical destruction of a multi-ton piece of equipment.
Has this actually happened, or is this just theoretical doomsday modeling from the papers?
Oh, it has absolutely happened. March 13th, 1989, a solar storm hit. Now, keep in mind, the 1989 storm was moderate compared to Carrington. Maybe a third or a fourth of the power.
And what did it do?
It hit Quebec, Canada. The geology up there is very rocky, the Canadian Shield, so the ground current had nowhere to go but up into the power lines. At 2:44 a.m., the currents hit the grid.
Oh.
In 92 seconds, the entire province went dark.
In 92 seconds, that is barely enough time to realize the lights even flickered.
From totally normal operations to total grid collapse, 6 million people lost power in the winter in Canada.
Yep.
Montreal was paralyzed, the metro stopped, the airport closed, school shut down.
That is terrifyingly fast. You cannot react to that manually. No human can flip switches that fast.
You cannot. And down in New Jersey, during that exact same storm, a massive step-up transformer at the Salem nuclear power plant melted.
Wait, at a nuclear plant?
Yeah, the transformer's casing bulged out like a balloon. The insides just turned to slag. That was one transformer during a moderate storm.
So let us scale it up. We get a Carrington event tomorrow. What does the map look like?
The research papers estimate that a Carrington-class storm could damage or destroy hundreds of these EHV transformers across the United States simultaneously, specifically in the Northeast, the Upper Midwest, and the Pacific Northwest.
Because they are closer to the magnetic pole.
Closer to the pole, and they have the wrong kind of resistive geology.
Okay, so the lights go out. A bunch of transformers melt. We fix them. What is the big deal? Why do you say this is an existential threat?
The big deal is the supply chain. You cannot just buy an extra high voltage transformer at Home Depot. They are custom engineered for each specific substation. They are wound by hand.
Oh, wow.
And they weigh between 200 and 400 tons.
400 tons, that is like, what, 200 cars?
You need a special rail car, a Schnabel car, just to move one of them. And here is the real kicker. We do not make many of them in the U.S. anymore. Most of them come from overseas, Germany, South Korea.
So we have to ship a 400-ton box across the ocean.
Yeah, and the lead time to order just one is typically 12 to 18 months.
Wait a minute. 12 months. That is a year-long waiting list for one transformer.
And that is when the factory is running normally, and you are the only customer in line. Now imagine the entire world is screaming for replacement transformers at the exact same time. The queue would not be 12 months, it could be years.
So we're talking about a scenario where large swaths of the developed world are just without grid power for a year.
Potentially, yes. And think about what that actually means. It is not just, oh, I cannot watch Netflix.
No.
Most gas stations need electricity to pump fuel. No fuel means no trucks. No trucks means no food in the grocery stores within about 3 days.
The logistics network just stops.
It stops.
Yeah.
Water treatment plants run on electricity. No power means no clean water coming out of the tap and no sewage going away.
It spirals so fast.
It spirals instantly. The papers looking at the economic impact estimate the cost to the U.S. economy alone would be between $0.6 and $2.6 trillion.
Yeah.
But honestly, in a multi-year blackout scenario, money kind of becomes an abstract concept. You're looking at total societal breakdown.
It sounds exactly like the plot of a post-apocalyptic movie, but it is just physics. It is literally just magnets and wires.
It is, and we have built our entire society on this quiet assumption that the magnetic environment of the Earth will just stay stable forever. We assume the ground beneath our feet was neutral. It is not.
But the grid is not the only thing at risk here, because we have assets in the sky now. We rely on satellites for everything. GPS, banking transactions, weather forecasting. What does a solar storm do to them?
The paper we read on satellite impact calls them invisible bullets. When the storm hits, it energizes the Van Allen radiation belts that surround the Earth. It fills them with relativistic electrons.
Relativistic, like moving at the speed of light?
Nearly the speed of light. Killer electrons. They can penetrate right through the metallic skin of a satellite and bury themselves deep in the internal electronics.
And what happens then?
This causes dielectric discharge. Basically, the satellite builds up a massive static charge on the inside, and then zap, it shorts out the motherboard.
So the satellite just fries from the inside out?
It fries. Or it suffers from TID, total ionizing dose. The storm dumps so much radiation so fast that the solar panels degrade instantly. The glass covers on the star sensors darken.
Oh, man.
The paper suggests that Carrington Event could deliver 10 years' worth of radiation aging in a single weekend.
So your brand new billion-dollar satellite suddenly thinks it is 10 years old and ready for retirement.
Exactly.
Yeah.
But there's a totally new threat that was not even there in 1989, the new space revolution.
You mean like Starlink, OneWeb, these mega constellations?
Yes. In the old days, satellites were the size of school buses. They cost $1 billion, and they were built like absolute tanks. Rad-hardened. They used old, chunky computer chips because old chips are tough.
Right, they can take a hit.
But today, we are launching thousands of small satellites that use commercial off-the-shelf parts.
So they're using the same chips that are in my smartphone?
Pretty much. They're way cheaper, they are lighter, and they are much faster to build. But they are vastly less protected against radiation. The study showed that for satellites in low Earth orbit, which is where Starlink lives, the rate of single-event upsets could increase by a factor of 10,000 during a storm.
Okay, what exactly is a single-event upset? Or an SEU?
It is a bit flip. A high-energy proton slams into a memory chip and physically flips a 0 to a 1.
And that crashes the computer?
It can. Or it can corrupt a command. It can tell the satellite to fire its thrusters when it absolutely shouldn't. And if the error rate goes up 10,000 times, the onboard error correction software just gets completely overwhelmed.
So we could end up with a massive cloud of zombie satellites.
Thousands of them.
Sure.
Drifting, unresponsive, potentially crashing into each other. It is the Kessler syndrome on steroids. No GPS, no satellite internet, no secure banking timing signals.
Wait, banking?
Remember, the stock market and global banks run on GPS time signals to timestamp transactions. You lose GPS, the financial sector goes blind.
Okay, I'm sufficiently terrified. We have the grid melting on the ground and the satellites dying in the sky. But in the research, there was something that somehow made this even worse.
Yeah. The Miyake Events.
This is the part that feels like cosmic horror to me. Tell me about the tree rings.
So back in 2012, there was a Japanese physicist named Miyake. She was studying ancient cedar trees. Now, she was not looking for climate data like most tree ring researchers do. She was looking at carbon-14 levels.
Carbon-14, that is usually for carbon dating ancient artifacts, right?
Right. But here is how it is actually made. Cosmic rays, which are high-energy particles from space, they hit our upper atmosphere. They collide with nitrogen atoms and turn them into carbon-14.
Okay.
And then plants absorb that carbon from the air. So a tree ring is basically a natural recording of the cosmic radiation for that specific year. If there is a lot of radiation hitting the Earth, there's a lot of carbon-14 in that specific ring.
Okay, so the tree acts like a tape recorder for space weather.
Exactly. And Miyake found a ring from the year 774 CE. This is during Charlemagne's time. And it had a massive spike in carbon-14, just a huge jump.
How huge compared to Carrington?
The data suggests the 774 event was 5 times more powerful than the Carrington event.
5 times. That is insane.
And then they found another one in 993 CE. And then, more recently, they found evidence of an event from 14,300 years ago that was twice as big as the 774 event.
So that one was 10 times the size of Carrington.
Yes. We call them solar particle events.
Okay.
If a 774 class storm hit us today, it would not just be the transformers cooking. The radiation would be so intense it would severely deplete the ozone layer.
Oh, wow.
It would expose high-altitude air travelers to massive radiation doses, like getting a full-body CT scan just by flying from New York to London. The energy deposited in the atmosphere would be equivalent to billions of Hiroshima bombs.
And we had absolutely no idea these things even happened until 2012.
None. We thought the sun was a relatively boring, stable star. We thought Carrington was the absolute worst it could get. But the tree rings told us that every 1,000 years or so, the sun just screams.
There is a fascinating side note about the Vikings in this research. It is a brief tangent, but it proves just how precise this tree ring data actually is.
Like the Alonso Meadow site, this is great. So we have known for a while that the Vikings reached Newfoundland, Canada. But we never knew exactly when they were there. Carbon dating usually has an error margin of plus or minus 50 years.
Which is a lifetime. It is the difference between saying my grandfather was here and I was here.
Exactly. But archaeologists found pieces of wood at the Viking settlement that had clearly been cut with metal tools, which the indigenous populations did not use. They analyzed the rings in that specific wood, and they found the 993 Miyake spike.
The cosmic fingerprint.
They found the spike, and then they just counted the rings outwards to the bark. There were exactly 28 rings after the spike. So 993 plus 28. We know for an absolute fact that Vikings were chopping wood in Canada in the year 1021 CE because the sun literally stamped a date on the tree.
That is incredible. But it also really underscores the point here. These events are real. They happen. And we have built our entire fragile civilization during a lull in the sun's activity.
We built our house on the slopes of a volcano that we thought was dormant. And now we are realizing the ground is actually shaking.
So we cannot stop the sun. If it wants to burp, it is going to burp. What can we do? We cannot just sit here and wait for the apocalypse. We have to have a plan.
We need the watchtower. We need a warning system that is far better than what we have right now.
Do you not already have satellites looking at the sun? I mean, I see pictures of the sun all the time online.
We do. We have satellites at a place called L1, Lagrange Point 1. It is directly between the Earth and the sun, about 1 million miles out.
It sounds like a pretty good spot. You have a front row seat.
It is okay, but it is downstream. By the time a CME hits a satellite at L1, the storm is only 15 to 60 minutes away from hitting Earth.
15 minutes. You cannot save the power grid in 15 minutes.
You cannot even get the utility CEO on the phone in 15 minutes. And there's another huge problem with L1. When a CME is coming straight at Earth, it is really hard to measure its speed.
Why is that?
From our perspective, it just looks like an expanding halo. Think of it like a baseball being thrown right at your nose. You see it getting bigger, but you do not have good depth perception on how fast it is actually coming at you.
You need a side view. You need to stand on the pitcher's mound and first base at the same time.
Precisely. And enter the European Space Agency's Vigil mission. This is the absolute game changer we have been waiting for.
So where are they putting this new satellite?
They are sending it out to L5, Lagrange Point 5.
Explain L5 to me. How is it different from L1?
Imagine a massive triangle in space.
Mm-hmm.
The sun is at one corner, Earth is at another corner. L5 is the third corner, trailing 60 degrees behind the Earth in its orbit. It is a gravitational sweet spot where you can park a satellite and it just stays stable there.
So Vigil sits way off to the side. It watches the space between the sun and Earth.
It sees the picture from the dugout. It can see the CME launch from the side. It can track the speed perfectly because it is watching it cross the distance. It can see the density. It effectively gives a stereoscopic vision of the inner solar system.
Let us look at the toolbox on this thing. What instruments is Vigil actually carrying? The ESA documents had a lot of acronyms, and I want to make sure we understand what they actually do.
The heavy hitter is the CCOR, the compact coronagraph.
Break that down.
So to see the sun's atmosphere, the corona, you have to block out the bright disk of the sun itself. It is just too bright. So the CCOR puts a little opaque disk over the lens to create an artificial total eclipse inside the camera.
I'm clever.
This lets it see the faint wisps of plasma ejecting from the surface.
So it sees the explosion the very second it happens.
Yes. Then you have the HI, the heliospheric imager. This is a wide-angle camera that tracks the plasma cloud as it moves through the void of space. This is crucial for mid-course tracking. It connects the launch to the arrival. It stops us from just guessing where it is.
And there was something in the mission specs about tasting the solar wind.
The plasma analyzer, the PLA, and also the magnetometer, the MAG. This is really cool physics. Because the sun rotates, the solar wind sprays out into space like a rotating garden sprinkler.
Okay, I can picture that.
The wind that hits L5 today will rotate around and hit Earth in about 4 or 5 days.
So Vigil is essentially tasting the water upstream.
Exactly.
Yeah.
It tells us the magnetic polarity of the wind days before it arrives. And that matters so much because if the magnetic field of the storm is pointing south, which is opposite to Earth's north-pointing field, they connect.
They lock together.
Right. And that is when you get the severe damage. If the storm's field points north, it might just bounce off our shield.
So Vigil tells us if the gun is actually loaded.
It turns a vague, generalized anxiety into a highly precise forecast. Instead of just saying, maybe a storm is coming, we can say a CME will strike in exactly 17 hours. It is south pointing. It will induce 100 amps of current.
And if you have that exact data, what can the grid operators actually do? What is the mitigation plan?
They can take defensive action. They can cancel routine maintenance. They can bring extra generation online to stabilize the grid frequency. But the big one, they can trip the breakers.
Wait, they can disconnect the long transmission line?
Yes. You shut off the grid intentionally.
You create a controlled blackout.
You sacrifice power for maybe 12 hours to save the multi-million-dollar transformers. Because if the lines are physically disconnected, the GIC has nowhere to flow. The transformers are safe.
So you basically turn a civilization-ending catastrophe into a snow day.
That is the ultimate goal. It becomes a manageable inconvenience rather than a total societal collapse. You sit in the dark for a day, play some board games with the kids, and then the storm passes and you flip the switch back on.
It feels like we are in a serious race against time, though. Vigil is not up there yet, is it?
No. It is slated for launch in the late 2020s, likely fully operational around 2031. Every single day until then, we're just rolling the dice.
We have to talk about 2012 again, because that was not just a historical discovery of tree rings. That was a near miss in real time.
July 23, 2012. The sun launched a Carrington-class CME. Massive, incredibly fast, highly destructive. It tore right through Earth's orbit.
But we were not there.
Earth had moved out of that specific spot in space just 9 days earlier.
9 days.
If that storm had happened 1 week earlier, we would not be doing this deep dive right now. We would likely still be trying to rebuild the power grid.
The economic impact would have been, what, trillions?
Easily in the trillions. We dodged a literal bullet by sheer orbital luck.
And luck is not a strategy.
It is not. The probability of a Carrington-like event hitting Earth is estimated at about 12% per decade.
That is uncomfortably high. That is basically a 1 in 8 chance every 10 years.
It is roughly the same probability as a catastrophic magnitude 8 or 9 earthquake hitting the West Coast. And we have strict building codes for earthquakes. We retrofit our bridges. We have emergency kits in our homes. But for space weather, we're still largely just hoping it does not happen on our watch.
It really puts our fragility into perspective.
Yeah.
We walk around with our smartphones. We panic if the Wi-Fi drops for 5 minutes. But the whole interconnected system hangs by a magnetic thread.
We live in the atmosphere of a variable star. We forget that because the sun looks the same every single day to us. But it has a temper.
The demons of 1859.
Yes. And next time, they will not just tap out gibberish on a telegraph wire.
Right.
They will silence the world.
So for everyone listening, when you hear about the Vigil mission getting funded or you see a headline about solar maximum activity, do not just tune it out. It is not just abstract astrophysics. It is quite literally the insurance policy for the 21st century.
Absolutely. And maybe, just maybe, look up at the sky occasionally. If you see the auroras in Florida, do not just take a picture for social media. Be ready.
A huge thank you to the researchers at Aalto University, the historians at the Science History Institute, and the engineers at ESA for the materials we synthesized for you today.
It is incredibly vital work they are doing.
I want to leave you with one final thought, a provocative nugget, if you will. We talked a lot about the Miyake events, those massive superstorms recorded in ancient tree rings. We only know about them because they leave a trace in carbon-14.
Right.
But what if there are types of solar events that do not create carbon-14?
The silent ones.
Exactly. What if the sun is capable of something even more extreme, something completely different physics-wise, that leaves absolutely no footprint in the trees? We are assuming the Miyake events are the ceiling of what the sun can do, but what if they are just the ones we happen to be able to see?
That is the ultimate unknown unknown, and that is exactly why we need to keep watching the star next door.
On that cheerful note, thanks for listening to The Deep Dive. We will see you next time.
Stay safe out there.